So what we're going to do is go over some of the basic skills you're going to need to go throughout the year. And this is skills for this class. This is not, obviously, if you go on to study engineering, the math you do is so much more than what you ever do in high school. And like you think AP Calc, even if you're like students in that class or preparing for engineering, that class, honestly, as much as it's good that they get a foundation of calc, it's a joke compared to what you take in college. Okay, so when you go to college, you'll see if you do end up studying either mechanical engineering, computer engineering, electrical engineering, civil, any of those main ones, even chemical does a decent amount of calc. Most of them do Calc 1, Calc 2, Calc 3, if not beyond. Mechanical does 1 through 4 really, and 4 is not called 4 at that point. It's called differential equations. But 1, 2, and 3 are taken by mechanical and civil. If you're chemical, you take 1 and 2. If you're a computer, you definitely take 1 and 2. I don't know about 3, probably 3. Calc 3 is really actually similar to Calc 1 and 2, but it's using 3 dimensions instead of 2 dimensions. Calc 1 and 2 only is 2-dimensional, x, y plots. Calc 3 involves a third dimension. It's functions of x and y. You ever seen like contour plots? You know what a contour plot is? Like a terrain plot. Imagine the terrain of some area. That would be using calculus 3 in a sense. The function, the behavior of it, would behave as a function of a contour in 3 dimensions. Like a saddle horse is an example of this. So the math skills we're going over now is stuff, honestly, for this class that I want you to know that you only have down pat. But it's stuff that you guys have seen already. So it's either from algebra, geometry, algebra 2, trig. It's in one of those areas. It's not going to be stuff from pre-calc because not everybody in here is in pre-calc. We're going to then go to Excel for a while. If there's one thing in this course that you take if you're not going to study engineering, it's Excel. A lot of the last 2-year students that are not in engineering have all said to me, like, the first thing, and this is like via Facebook messaging and stuff, hey, I thought I mentioned to you that the Excel stuff that we learned, I use all the time. Schulte sent me a message recently, because he's in business school there, or he's not studying engineering. What is Schulte studying? Anyone know? I know Scarangello, Elliot, is studying astronomy or astrophysics, one or the other, I forget what it is. Did he change?
He's doing geography.
No, he's not. Geography. What? As a major, really?
Yeah, it's a video game team.
Interesting. Anyhow, all I'm saying is you're going to use Excel in any major you are in college. So if you're not going to go on to be an engineer, and you're thinking like, oh, I don't really need the skills so much. Excel, the stuff we learn here especially, will be useful for any major you use Excel for. In addition, when you go to work later in life, you have to use tables, you have to use presentations. So as much as maybe Excel is not the one your company's going to use, the ideas behind the formulas and the way you can tabulate things and let the tables do all the work for you is what we're going to learn. We're going to learn about functions. We're going to learn about like editing formulas, making tables that can calculate things on their own. So that's the important stuff. It's not going to be about like how to make a pretty table. That you can learn on your own. You can change colors. You can change format. We're going to do the math behind Excel. We're also going to start a project soon. We're going to have 2 projects that are out of this. Remember that book I told you to buy, When Will I Ever Use This? You should bring that into our next class. In the next class, we're absolutely going to start using it. We're going to start one of the first projects in that book. When we get to the second project, it's also going to involve Excel. And it's kind of a cool project. Remember I've talked about optimization, minimization, maximization? Imagine you had a workforce and you wanted to maximize the profit based on the hourly rate you have to pay people, based on the requirements of people you need at the job. You can run a program and write the program in Excel in order to solve for the scenario that gives you the maximum profit or minimum cost. It's kind of cool. Excel has something in it called Solver. When I was in grad school, I took a course in engineering called Optimization Techniques. And the teacher was obsessed with Excel, like obsessed. It was nuts. And personally, when I was in college studying undergrad, we didn't use Excel except when we were like having data calculations and stuff. But we didn't use it for optimization, for calculus. Turns out that it can do all this stuff extra. So I learned about it in grad school. And then this past summer, I took a course, which is where that book that I'm having you get comes from. And we're going to do the projects out of that book, actually. That's going to involve Excel also. We're going to talk about statistics for a little while, ones that apply to engineering. We're going to talk about rates of change and slope, and then measurements and instrumentation. Okay, and that's using technology and tools to measure things. So we'll talk about a caliper, different devices used to measure in engineering. Let's start with general circle and polygons. First, 3 terms: diameter, radius, circumference, or 4 terms: circumference and area. We should know all of these. I'm going to quickly write these up. If for some reason you're like, I have no idea what you're talking about, please ask. But right as of now, I'm assuming you know this stuff, so I'm just going to kind of fly through it a little bit quickly. So obviously, we're going to start with the circle. Yeah, I'm terrible at circles, so I thought, why not, right? Let's go ahead and draw a diameter. Shows up nice there, right? What's wrong with that? Oh, that I used the circle feature? Or? Let's draw a radius. What? I have R, the radius. I put the radius on its side, I guess. Just put it the other way. Here's our center of the circle right here. Circumference. Formula, quick. Circumference? 2 pi r. Okay, or? Pi times? Pi d. Tom, area? Pi r squared. Spoke too soon, Mr. Reynolds. Okay, those are the 2 formulas you need to know. You got to know these in general, honestly. Even if you don't study math, you don't do anything with math in the rest of your life. If you need to calculate something that's a circle, you need the area, you need to know the square footage of paint you're going to put in a certain area, and there's a circle there. It's very useful to know how to calculate the area of a circle. It should be something in everyday life that although you're not using, you should know. Okay, even circumference. Questions? No? Good. Concentric circles. What are concentric circles? Use your root words. Yeah, they share a center. Very good, Sam. They share a center. So we've got circle number 1. We've got circle number 2. And they share a center. Okay, now, each of these has a radius. This is called the inner radius. And this is called the outer radius. Usually with circles, we designate the radius, and we've seen that a lot in math. In engineering, you use diameter a lot. You also use something called a hydraulic diameter, which is taking a cross-section of like a pipe that's not a circle and giving it a diameter or an equivalent diameter. Imagine a rectangular cross-section. Like if you think, well, these lights, if you think of their cross-section, they're rectangular the whole way. They're not circular pipes. In the ceiling, there's ductwork. The ductwork carries air and ventilation. What the hell are the vents? They gotta be. Do we not have vents in this room at all? Well, we have air conditioners. That's what's keeping the room cool, and we have radiators for heat. So that's why there's probably no ductwork in here. But traditionally, you'll see that there's ductwork in ceilings. Maybe there's none in this building because it's probably that's how you see in movies that they can. But if a person did go through those, what would happen? They'd fall right through. It's not. There's not enough strength to hold a person. There's barely any strength. You just hold the structure itself. The live load of the structure, or the dead load of the structure itself, is something that is only supported by like a thin piece of metal. It's like screwed into the top. That's all fake. You can't really climb the
So all those movies are not real?
Yeah, they're not.
It's like in the office when he throws like they like climb into
The cat and it comes out the other side. I love the office.
That
Next.
was so funny.
Pretty much, I saw a video yesterday that said what you said about the bridge that fell was wrong.
What bridge? Roman Errors?
Yeah.
What did it say?
Well, what did you say? What was the cause of the bridge falling?
The natural frequency of the bridge vibration were reached.
Maybe, I don't know, but they said that that's not, didn't have anything to do with that.
What did it have to do with it?
It said it had to do, I don't know, they didn't explain it more, but
Is it possible that what you read is about natural frequencies, but you don't know the terminology?
The wind would hit it,
Yeah.
and then it would turn, and then the wind would hit the back, and then it would turn again.
And what happened eventually? It reached its natural frequency. So natural frequency of ever seen an opera singer sing and the glass breaks?
Yes.
The natural frequency of that actual material is what the opera singer is reaching,
Yeah, they
causing
said that's
vibrations.
they said that's not what it was.
Did you see the oscillations at the end become uncontrolled? That's what happens when something reaches its natural frequency. I'm not lying to you, I promise. Sure, the wind caused it to sway, Nick, absolutely. But again, what caused its failure, its utter failure in the end? The vibrations and the oscillations reach natural frequency, so they become uncontrolled. It's called chaotic behavior. Yeah, that's exactly
it.
it. Is.
You're being controlled.
The description is called, it says teacher.
What does it say? I'm curious.
It's 1 minute. I'm just gonna play it out loud.
You don't even know what it's.
While I've heard that in Seattle they just call it bad bridge building, most teachers in physics textbooks have probably told you that the bridge collapsed because of resonance with the wind. But they're wrong. That's because a resonance is a vibration driven by a source oscillating at a similar frequency, like how a swing in the park goes higher and higher as you push it, or the electrons in an antenna move in tandem with the electromagnetic waves of a radio signal, or how a guitar string vibrates or wine glass shatters if you sing at just the right pitch. And that's not what happened at the Tacoma Narrows, because people at the bridge that day measured the wind speed as being fairly constant, or not oscillating. So there was no forced resonance. It's also tempting to think that the bridge collapsed because of vortex shedding, a cool-looking fluid process where vortices take turns sloughing off the edge of an object. But that's not right either. What did cause the bridge to collapse is a phenomenon called air elastic flutter, the same thing that causes a strip of paper or blade of grass to vibrate if you hold it tight and close straight at the edge. Basically, with enough wind speed, the bridge started to twist a little bit, but then gravity and tension in the bridge caused it to twist back down, except too far. So now the wind can push it in the opposite direction, causing it to twist more violently, and so on and so forth until, well, the bridge flooded itself into destruction. And air elastic flutter isn't just limited to bridges. It can cause airplane wings to hum annoyingly or vibrate so vigorously as to
I want to read what it says.
But don't worry, the last time this happened on a commercial airplane was in the early 1960s. You should probably be more concerned with the haunted swing set in Fremont, Argentina, that can swing on its own for days. Oh wait, no, that's just aeroelastic flutter. Sorry, ghosts. Physics just blew you away.
If that's right, it's good for him. But I literally learned in college that it was that. So I mean, I could go back to my professor and let him know that he was wrong. And say, but I'm dead serious. That's exactly what I learned. Because we learned about natural frequency in engineering. And when certain things happen, like the wine glass for the example, the molecules themselves, the behavior of them becomes so unbounded that they start to go out of control. I've never. It could be both. I don't know. Honestly, I've never heard of aeroelastic flutter, and I didn't like. My thing wasn't really fluids, and that would be fluid mechanics. I don't know. I'll look into it then. Thanks. Do you want like a pat on the back that you just proved?
No,
Because that's what it looks like you're looking for.
Because I had no idea what he was talking about. So like.
No, it's good that you brought it up. That is good that you brought it up. So there's definitely something else. I'll look into it for sure. Thanks. Hey, concentric circles. What else do we need to think about for concentric circles? Why might I choose this as a topic that would be important? Why would concentric circles be something that would be important?
Domes.
What do you have? Domes. Okay, I guess there are circles. The dome is a circle, and then another circle, and then another getting smaller and smaller to the top. That is concentric. Or a pipe. What else?
Overlapping areas.
Because the areas overlap. So what else could we maybe have to do? Why would we want to know anything about concentric circles?
Oh wait.
Sections of circular stairs.
I can't hear you. You're right on the track with measurements, that part. Not necessarily fitting into another, but something is going to fit. Like, if you think archery, if you were an archer,
Like measuring the area of the network, for example. So you subtract the whole area minus the blue area. So
yeah, why might you want to know the area of the red region?
if you're constructing like a building that's only like a circular motion, but it's like there's nothing inside.
Okay, so for materials, that's what I was kind of getting at. Manufacturing, a lot of things with manufacturing have to do with the necessary area and volume of this like outer shell, where the inner part is left empty, or it's like, think about even copper wires that have that like rubber insulation on the outside. This is the rubber insulation here. Pipes that carry water. This is the actual pipe with insulation keeping the water cold or hot. There are so many applications of concentric circles because you have circles within circles all over the place. Your tire with the hubcap. I mean, it's insane. Paper towel rolls. There's so much to do with concentric circles that alone, that topic, you're going to see apply all over the place. So make sure that you understand how to calculate things with concentric circles. Okay, how would I calculate the area of the outside again, Klaus? The red region?
So it's the area of the whole circle minus the blue area.
Okay, the red region on the outside is the total area minus the blue area in the middle. It gives you what's left over. Okay, that's really the only reason, there's the only way you can get it. What else about concentric circles I want to know? There's a term called wall thickness. I don't know if I'm going to describe it in the next one. No. Wall thickness. How would you figure out the wall thickness with concentric circles? If this were an object and there was an outer wall and the inner part, how would you figure out the wall thickness? What would you do?
If the circle is inside of the wall, find the area of the whole circle first and then subtract that from the area.
Close. They're thinking area. That's what you just did up top. So wall thickness, though, is not area. It's not a measurement of area. It's a linear measurement.
Do the radius on the inside.
Switch it around.
Which one are you measuring?
If we want wall thickness, if I want the wall thickness,
To get the distance between, yeah. So you subtract RO from
okay, very simple, obviously. Outer minus inner radius. If we want the wall thickness, why might the wall thickness be important? Insulation, very good. Think back to at the end of the year last year, we talked about heat transfer, and one mode of heat transfer was via conduction. There's conduction, convection, radiation. If you have a thicker wall that's insulating, you have a greater thermal barrier. Thus, the coolant or the heated fluid will remain at the temperature it is while traveling through the pipe. If you have a hot water pipe that is not insulated and it's running through like the course of several yards, feet, meters, whatever, it's going to lose temperature as it travels through the pipe because the pipe is metal. Metal is a conductor. The conductor takes the heat, gives it off to the outside environment. So you need a lot of insulation. The wall thickness there, T, is the insulation. All right. Let's take a quick look at tangent lines. You've seen tangent lines. I want to talk about some quick applications of tangent lines. Let's see. First, we talk about these? No, we did not talk about these last year. The year before I did in physics. So, the first and most useful thing for tangent lines are pulley systems. So in a lot of devices, you're going to see pulley systems. And the cords themselves that are going around the pulleys are tangent to the actual pulley itself. So if you're in the fitness center and you're lifting weights and you see that this is the setup, here's the weight stack right here. And here's the handle at the end. Okay, it's a great drawing, right? So you pull on this handle here, which goes underneath this pulley around the top. What does it do? It lifts the stack of weights. So what does a pulley do? What does a pulley do? The pulley doesn't lift something off the ground. It does provide mechanical advantage time. Right now it doesn't, but it does. If you change the scenario, you can definitely get mechanical advantage out of it. That's one of the huge things. Okay? It can move things, but be more specific about what it's actually doing, because you're displacing weight. The pulley's not displacing weight. Follow what I'm saying? What is the pulley actually doing? What is the pulley actually doing? It redirects the motion of the force applied. Ready? I'm at the row machine, pulling back. Which way am I pulling? Horizontally. Which way are the weights lifting? Vertically. How's that possible? A pulley. A pulley traditionally redirects the applied force to a new direction. That's what it really is there for. But these have, again, tangent lines. The cords themselves are tangent. Conveyor belts. Conveyor belts. Have you ever seen a conveyor belt before? Think about like a tank track.
I feel like
I know, my animations are great, or my drawings are wonderful. So think about something where it's going along the conveyor belt the whole time, obviously be a platform to keep it sturdy. So here again, on the end, you have taut tangent lines. Okay? What other thing?
Escalators too.
No, they have what?
Escalators.
I don't know. I've seen the escalators when they repair them, and I never actually stopped to look inside. I have to do that sometime, or maybe look it up. You think that is there a conveyor that runs the whole way through? Is that what you're saying? It would make sense because when you put your hand on the handle, right, that goes back down and around.
Yeah.
So that's got to go back around. So there's some sort of cyclical motion there. I don't know. Yeah.
For a final engineering project, can we make a giant hamster wheel and then we can make electricity?
Like a human-powered one?
Yeah.
As long as Koenig runs in it the whole time, we're good.
I can run it.
He woke up. As long as Nick runs in it the whole time, we're good. Is that a deal, Nick?
Yes.
So you agree?
Yes.
You sure you know what you're agreeing to right now?
It's like the same thing.
So it is recording, yeah. So at the end of the year, you just agreed to that. You're sure, right?
What?
You agreed to it, right?
Yes.
He agreed. He agreed.
Hey, what?
Well, let me ask what he agreed to. He agreed to it.
I'm so confused.
It's probably a giant conveyor belt with a little like locking.
Yeah, it's the same thing. Only just
I've seen that also. Have you guys ever seen? It's kind of cool. Have you gone to a Costco in the city where it's several floors?
What?
You ever go to Costco?
No, when
Oh, yes, but it's
Have you ever
one.
gone to Costco?
It's a warehouse.
If you've gone to Costco before in the city,
No.
you can actually go to the second or third floor by putting your cart,
Oh, they have
and
that
it
in the
takes the
park.
cart up. It's cool, isn't it?
They have
You
that.
put your car on one of the escalators, it locks in like that, and it locks into it. It pulls the car up for you.
It's
and you
between
leave it
all
at
of
the
them.
top.
It's in between both of them.
What?
In between.
With both of the escalators.
Oh, is that where it is? Okay. Yeah, so the escalators that go up and down here, and then the car goes in between.
Yeah.
Yeah, it's kind of cool, but it's the same idea with the conveyor belt. Hey, the last reason we need to know about tangent lines, we're going to get into 3D AutoCAD soon, and when we do that, you're going to have to think about tangent lines when you want a curved surface. So if you have an object like this, but you don't want it to be a rigid corner, you want to round it over. This is called a fillet. That's a terrible drawing. This is called a fillet. Okay, where the actual corner is rounded over. This line here is tangent to a circle that's not even there. Imagine, for a second, this is not there. It's called a construction line, what I'm about to draw. There's a little circle here that those two lines are tangent to. That's how the computer mechanism works this way. So we're going to have to understand how this tangent function works. You're going to do a lot with tangent with AutoCAD. Okay, but there's like a construction circle here. This is not an actual object. It's a dashed line. It's called a construction scheme or construction line.
Can I show you the flash drive I got?
Sure. What else? All right, quickly to the next topic, quadrilaterals. I'm going to give you a little family tree of quadrilaterals. All you need to do is remember what each quadrilateral has as a property.
You watch the
Lilo and Stitch. Yeah, I know what that is. So the general quadrilateral is the four-sided polygon. Okay, we start with that. It can be any shape as long as it has four sides. Okay? That kind of has five sides. Okay? It kind of looks like a parallelogram. I didn't want it to. Isn't that weird how you like try not to draw a parallel and you do? That's so funny. So we have a general quadrilateral, no parallel sides, no right angles, nothing like that. After that, we go from quadrilateral. What's the first type of four-sided polygon that's like the general part of the family tree? That's the ending of the family tree. The beginning.
Trapezoid,
Why trapezoid?
because it only has two parallel lines.
All right, so we got trapezoid over here. Two parallel sides. That's all we gotta know about a trapezoid. A of a trapezoid. 1/2. You know why this is the area, Miles? I was gonna ask why. And what are you doing by adding them and dividing by 2? Averaging them. Think about it, it's an average. Add 2 numbers, divide by 2, it's an average. You're averaging the bases times the height. Base times height is the area of a rectangle. So literally that's all you're doing. You're finding the area of like a rectangle here, but by averaging the bases. Now that branches off, so that one branches off on its own. Now we go to the right side and we've got parallelogram. Parallelogram has a lot of features to it. A lot of features. What are some of them? Yeah, parallel sides. Thank you for the obvious one. Good. That's the one that we just always have to say because nobody seems to say it. What are the actual other features, though? There's a lot of other ones. Opposite angles are congruent. What else? Opposite sides are also congruent. Is it the congruent sign? Right? From geometry? Equals with a squiggly?
Approximately. Or is that?
That's an equals on the bottom, sorry. It is.
Oh,
Yeah.
both squiggles.
What else? Consecutive angles add up to 180. Very good. Consecutive angles add up to 180.
The diagonals are equal to each other.
The diagonal's not equal, but it's something about diagonals. What do they do to each other? Bisect. Question? Okay? So what we drew on the diagram, obviously, and then those 3 there. Now, from a parallelogram, what can we get? From a parallelogram, what are the 2 options that come from there? There are 2 types of special parallelograms. What are they? Close? Rhombus and a rectangle. A square is the combination of those 2. So next, I know, right? You guys didn't see this in geometry ever? Here's your square. Here's your rhombus. Here's your rectangle. You got a rhombus and a rectangle. Now, the rectangle, first of all, the rhombus and the rectangle have all of the properties of the parallelogram above, in addition to the ones I'm about to state. So a rectangle has 90-degree angles. A rhombus has 4 equivalent sides. A rhombus's diagonals are perpendicular. Although it's not obvious there. That's a terrible drawing, but these diagonals are perpendicular. A rectangle's diagonal are congruent. It's hard to draw congruence there. Okay. Now again, it has all the ones above as well. The last shape is a square, and a square simply puts all of these properties together. A square is a combination of a rhombus and a rectangle. A rhombus and a rectangle. Why am I handing on this? Because a lot of the shapes that we're going to see this year, a lot of things with civil, specifically engineering, you're going to see you have a lot of quadrilaterals and triangles. Because again, what are 2 triangles really just together make up? 2 triangles together. Yeah, quadrilateral. In general. I'm not saying right triangles. Just 2 triangles put together always make a quadrilateral. And 2 triangles together is one of our most stable structures we're going to see. Okay, if we had a structure, we'll talk about that actually later when we get to the building. When I get into it. Quickly, regular polygons. All you have to know about them. The interior angles of a regular polygon could be very useful for you to know. And there's a formula for that. So say we have a hexagon here. Yeah, you guys are good. N minus 2 times 1/8. I heard a few of you say. Okay, this will give us the sum of the interior angles. So each angle, you just divide it by n. That's each angle, okay? The numerator is the sum of the angles. We add them all up. So if you want each individual angle, just divide by n. Right. You've seen it prisms like this. Yeah, that's what you've seen before. And most people think that's a prism. And that's an example of a prism. But when we talk about 3D solids in this class, we're going to talk about shapes that are prismatic and shapes that are not. If a shape is prismatic, if it's prism, it makes it very easy to make a third dimension from it in our CAD program. So what we want to think about is the definition of what a prism actually is. So that's a prism. So is this. This is not a prism, this next shape. How would I draw this? Okay, so the top two are prisms, the bottom one's not. So by definition, what's the differences, or what do you see? What characteristic or property?
One of them, well, the two of them that you did first have the same shapes on the top and on the bottom, of equal size.
Exactly, that's exactly right. The bases are the same. So, in this first shape here, these are both exactly the same triangles, and they're connected. These are the exact same circles connected. This, clearly, is a little square or rectangle. This is a much bigger one. This looks like a pyramid almost, but without coming to the point at the top. So a prism is a three-dimensional shape that connects two congruent bases. Two congruent bases. Okay, the bases in the top one are circles. In the middle one are triangles. This is not a prism. We are going to look at shapes like this, though. And there are ways to connect two shapes that are completely different. It's actually really kind of cool. In AutoCAD, it's not called AutoCAD anymore, it's called Inventor. But in CAD, in your program, what they'll do is they'll interpolate the actual in between. So if you put like a circle on one end and a square on the other, it could actually connect those. It's kind of weird, but it will be able to. And we're going to see that term. It's called lofting in CAD. But we're going to see that lofting command, and it allows you to do that. Specifically, though, for these, we're going to see in CAD, it's called an extrusion. You take a base and you extrude it in one dimension, or in the third dimension, another one dimension. Now, what I do want to talk about with prisms in general is the volume of a prism. The volume of a prism. And many of you don't know how to find the volume of a prism. Many of you know how to find the volume of specific shapes. So we all know this one. How do I find the volume of this? What's the volume of a rectangular prism? What's the volume? LWH. Everybody knows that, right? Okay, let's prove where that comes from though now. Not prove, but show. All right, now we look at the third dimension. We can see it a little bit more. See what I'm shading? I'm about to shade this region right here. I'm shading that bottom face right there. If I were to think about this shape, I could think about this shape as a prism where the top and the bottom are identical. See what's shaded in red? Those are identical faces. They're both the bases of the prism. And if I think about this, the volume of this prism we said was LWH. LWH. Well, I could leave H alone. What is LW really? Of what? Yeah, the red shape is the area. Think of LW as the area. So we could say it's the area of the base, really, times the height. Here's your formula for any prism, okay? The volume for any prism whatsoever. If you could find the area of one of the bases, and then just simply multiply it by the height. Area of the base times the height. So if I scroll back up a little bit, yeah, Sam, go ahead. No. So you take the one area, and you simply multiply it by the length that it's in the third dimension. Okay? So let's look at the example of the cylinder. What shape is on the end of a cylinder, obviously? What shape? What's the area of a circle? Oops. What's the area? Pi times? So therefore, the volume is pi r squared h. Okay? So we're going to see this with the second line here. This is the formula you were given in your SAT, in your math class. Where does it come from? It comes from the area of the base, which is pi r squared, times, you could call it height or depth. Any word is fine there, it doesn't matter. In your CAD program, it gets stuck all the time, so you know. In your CAD program, you might call it the extrusion length. Extrusion length. In CAD, if you want to make a prism or a 3D solid, if it's prismatic, all you got to do is make one of the bases. And then you just press one button that says extrude, you give it the extrusion length, and it takes a circle, and it makes a cylinder out of it. Or it takes a square or a rectangle, and it makes a rectangular prism. Or it takes a triangle, or whatever shape you pick. If you want to make a pipe in 3D CAD, you want to make ductwork and piping system, you make 2 concentric circles. And then you only take that wall thickness and extrude that. You don't extrude the middle. See what I'm saying by that? So if you wanted to make a pipe with an opening, okay, you shade in this region, or you select this region in CAD, and you press extrude, and it will extrude it by a certain dimension. It will leave the middle of it open. Okay, it'll leave the middle of it open like that. All right, applications of this. 3-dimensional prismatic solids, applications. They're everywhere. They're everywhere, literally. Your 3D printer works via extrusion. That's literally how these work. They heat up the filament, and they push it out the nozzle, and what shape comes out? A cylinder. It's a continuous cylinder coming out that it lays down in lines. That's how it works. If you were to let the 3D printer warm up and it just keeps spitting out filament, you'll just see string pouring out. And it's literally a cylindrical shape the whole time, pouring out. What else? Okay, so great examples of these. This radiator is not a good example, but some radiators have what are called pin fins that come off the end of them. And they're literally cylindrical shaped objects coming off the end. They allow to increase surface area so that the radiation, so that the convection can occur more efficiently. The more surface area, the more convection you have, the more heat can heat up the room. That's why if you look at these radiators over here, look at all the surface area. Notice this isn't one block of metal. There's hot water running, not now, there's hot water running through the pipes. All this surface area is what radiates heat. Via convection, really, actually. It's called a radiator. Technically, I would call it a convector. It does involve radiation, but mainly it's airflow over the actual radiator that causes convective currents in the room. And those convective currents cycle in the room. Other stuff, there's a lot of other things. Screws, bolts, nails, all those things, a lot of them are extruded. And then how are screws made? They just have a threading process that threads the actual threads onto it. But a nail is an extrusion process, comes to a point. Where you guys have seen extrusion all the time. Where have you seen it before? Where you have some sort of a shape and then a prism comes out that shape. What? A door. What do you mean by a door? Give me more. It's a rectangle in 3rd dimension. So you think about this, if it's a wooden door, it's easier. You see a rectangle, and then it's extruded like maybe, 2 inches, whatever the thickness of a door might be. Literally everything around you can be thought of as a prism. This tabletop is a prism. You can think of this as a base, and this as a base, and then this is the extrusion length. Or this is the base, and the bottom is the base, and this thickness is the extrusion length. It doesn't matter which way you go for a rectangular prism, okay? How many of you have ever made like homemade spaghetti, or have ever seen someone make homemade spaghetti? Ever see them put it through this thing? Either they have this little wheeling device and it comes out the end, or they push it through and it comes out like the end. That's extrusion, that's all it is. The Play-Doh shaped things, that's a great example, Nick. You put the end of the shape and it was like a triangle, you would push the Play-Doh through and you would get this log that was like a triangular prism coming out the end of it. It was kind of crazy. But that's extrusion, okay? We're going to see this again in our CAD program. Symmetry. We need to understand the concept of symmetry by reflection, rotation, those two things. We're going to use them in CAD. Imagine, right, you design a building, and the other half of the building, or the next building over, is identical. Are you going to want to redo the whole thing? No. You might put a construction line and make it symmetric. Or maybe on AutoCAD one day, I don't know, I did this last year, I had students create something for like Christmas for their parents or something. So say you want to make a little Christmas tree. You could design half the tree and then do what? Reflect it over the vertical axis. Okay, so we need to understand the concept of reflection and rotation. There is symmetry via rotation also that exists as well. How do you have symmetry via rotation? So let's say you have, last year Kevin and Marcelino were trying to build this like homemade drone, and they were actually 3D printing all the parts to it. The actual structure, the 3D printing part was really, they did a lot of great work. The actual final product was not really very good, but the actual structure was phenomenal. They never finished their final product. Let's say I needed 12 holes around the edge of this, all of circumference of 2 centimeters, or diameter of 2 centimeters. You could physically make one of those holes, and then you could put a center axis right here, a dot, and you could say, I want 12 of these about that dot. And it would literally rotate and put 12 holes, the exact same space, or perfect spacing. Say you make it 13, it'll space it out even better. 14, it'll respace everything until it's physically impossible to fit as many more holes. But you can have, again, symmetry via rotation also in CAD. You can have simple ones with like 4 windows to put one window, and you can get to repeat the pattern to each of these. Okay, but it's symmetry that we're talking about here. You can ask a question or no? I think you're okay. Let's see. I want to jump into Excel, but I'm going to skip it for a moment until Caroline comes in. She's at a college visit. I'd rather nobody miss Excel, because when you miss stuff in there, you're going to fall behind. So on the next slide, I start talking about Excel, right? Oh no, triangle still. Sorry, I skipped ahead. Area of any triangle. For a what kind of triangle is that though? Right, for a right triangle only, okay? Now, I shouldn't say only, because any other triangle, if you could figure out the height, and you know the base. Okay, we know that one, right? Now that's a general rule. I'm going to give you another formula that you may or may not learn this year in your math class. I honestly don't know if you learn about this. The other formula is a lot simpler. Okay, it's very similar. It's where this formula is what gives you this formula actually, just so you know. But it happens to be a 90-degree angle, so you end up with a sine of 90, which is 1. So take a look. It's the same formula. You all see that? If the angle C, capital C, is an angle, if the angle C is a 90-degree angle, sine of 90 is 1, so therefore it's the exact same formula. So in this case, this is for any arbitrary triangle. If you know 2 sides and the angle between. So again, this is capital C, this is capital B, this is capital A. All you need to know are 2 sides and the angle between. Okay, jot that down, please. A and B are 2 sides, C is the angle between. So if I have sides B and C, I need angle A. If I have sides A and C, I need angle B. It's always 2 sides, the angle between. 2 sides, the angle between. So this formula, although I write A, B, sine, C, it can be any orientation. If you have 2 sides, the angle between, you've got the area. Either this or this. These 2 and this. Doesn't matter what you have. Yeah, it's similar. It comes from the law of sines, actually. It's a good derivation from it. It comes from the law of sines. Remember, A over sine A equals B over sine B equals C over sine C? Did you learn the law of cosines last year also? Those 2 formulas are where this comes from. Did you learn this last year?
Not that one.
Okay. So the area, yeah.
We did the area.
Okay. Good. You know Pythagorean theorem. I really don't need to go over this. Who knows 3-dimensional Pythagorean theorem? That's 2-dimensional. Anybody know 3-dimensional Pythagorean theorem? This is something that could be useful for you, actually. 3-dimensional, so I'm referring to a solid. 3-dimensional Pythagorean theorem. I'll give you an example, okay? This was an SAT problem years ago I saw. Imagine you have a rectangular solid. And you want to know the distance. Let me leave the labels. A, B, C, D, E, F. Oops. Damn it. G and H. Each vertex, I'm giving a label. All right, if I wanted to know the distance between A and F, that segment, A is in this corner, isn't it? F is in this corner. So technically I'm going through the prism from one corner all the way to the other. You see what I'm saying? So if I can't, it's hard to show this in a diagram. I'll show you with the box. It's very simple. So take a look back here real quick. Look at this box. Okay? I'm asking you via this to find the distance between this corner right here and this corner back here. See how it's diagonal? See how it's diagonal? This is three-dimensional Pythagorean theorem. A, B, C, D. So extend Pythagorean theorem. A squared plus B squared plus C squared equals D squared. Does that make sense what I'm saying right now? And if you want the diagonal across the prism from one corner to the other, it's A squared plus B squared plus C squared equals D squared. And I'll highlight that. I know I just showed you in the room, but for the video, so later, ready? So it's going to be this squared plus this squared plus this squared, meaning length squared plus width squared plus height squared equals the diagonal squared. Okay, L, W, H. Let's call those LWH. Okay, L is this. I'll put it in black. L, W, and H. D is the dashed line from one vertex to the other from each corner of the polygon, of the solid. That would be useful when it comes to 3D design. Okay, if you need to know what that distance is for some reason. And last year, 2 groups actually had projects in which they put supports through, and they needed those supports to be a certain distance. So they needed to know what that actual distance was. So I kind of add on every year to the math stuff that you might need based on what some groups do or projects, thinking about, okay, they might actually need to know this. And some of the stuff I know you know already, I'm assuming. You know this already, I'm reviewing it. So Katoa, you should all know. You should know how to find an angle or a side of any triangle. Okay? In case you're confused. Opposite over hypotenuse is side, is sine. So if I were to look at this angle theta right here, and I wanted to know what the sine of theta was, okay, it would be opposite, which is B, over hypotenuse, which is C. An itch on my nose. It's killing me. So the opposite is B, hypotenuse is C, B over C. How would you get theta? How would you get theta?
Inverse sine.
Very good. Okay, always take the sine inverse. We did this in physics last year. You also did it in math. Any questions so far? All right. Now I think, yeah. Now I want you to skip ahead. We'll come back to Excel in a little while. Skip ahead to... What's the next topic? Statistics? Yeah. Skip ahead to statistics. Skip ahead to statistics. By the way, over the weekend, be prepared. I'm giving you a reading assignment. Today is day 3. I see you again on day 6 or 5? 6? So you have a couple days. So it's going to be a lengthy assignment. What do I recommend you do? Yeah, I see you day 6. So that's Monday, Tuesday, Wednesday I see you. So this next homework is not due till Wednesday. It will be lengthy. It will be lengthy. Friday, Saturday, Sunday, Monday, Tuesday. You have 5 nights for this next homework. So expect it to be lengthy. So when I give you a lot of reading, it doesn't mean cram the period before. It means do the reading. The reading is going to be a lot on Excel, and it will help you when it comes next week when we're working with Excel. I will most likely introduce Excel, provided Caroline gets back, which I think she will soon, in the second period, and we'll go over some of the basics, but the reading will be from Excel, and then there will also be a reading based on statistics, okay, on this stuff that we're going to do now. First, probability. Probability. What is probability? What is it? Well, how do you describe probability? How would you describe it? Sit your hands. You know how to describe probability? You should all be able to describe probability. What is it really?
It's like the outcome of something that.
Give Give me an example.
Like, say if you had 10 apples.
Okay?
Classic math problem.
Yeah,
10
right.
apples.
Classic terrible math problem. There's 10 apples, right?
And you take away 3. So you had 7 out of 10 apples.
Okay, so let's pick colors then. There's 7 red apples and 3 green. What is the probability of pull a green apple from the bag? 3 out of 10, right? That's the traditional probability question. So probability is what?
The chance of something
The
happening.
chance of an outcome occurring. That's what probability is, right? The chance of an outcome occurring. Chance of an outcome occurring. Is that clear what it is? All right, I don't have to go into detail. We're going to use this concept in Excel. I'll show you where it'll come into play, but you need to understand the physical definition first. How about frequency? How about frequency? What does that mean?
Like sine waves or just in general?
Not with sine waves, I apologize, with statistics.
So it's like how often something will happen.
Yeah, how often something happens. So you used to say, I don't frequent the store often. People don't use that word anymore though, you notice that? They say I don't go to the store. The right word would be frequent. I don't frequent the store often, meaning I don't go to. It's actually, it actually means the same thing. How often you go there. So frequency for data is how many times a data or datum occurs. Data is plural by default. Did you know that?
No.
You know when you do that? Data, the word data, you say present your data, is already a plural. Data, the word data, if you're talking about one piece of data, I think it's D-A-T-U-M, datum. I think that's the actual singular form. You can look it up, check if I'm right. We know Koenig looks, so it's fine. So is it data or datum? You didn't even listen to what I was saying. I was about to say you know
No.
right.
You were saying to look up data, and so I could prove you wrong.
Oh, good. There we go. Prove me wrong. Come on. So I think it's datum, but if it's not, please let me know.
Yeah,
It's bad.
So how many times one datum occurs? How many times it occurs in a full set of data? That's the frequency. That's the frequency. Okay? We're going to talk about histograms at some point, and you can see what a frequency histogram is, and specifically something like a cumulative frequency histogram. I'm going to skip the next one. This is where I talk about cumulative. I'll talk about that in Excel more. Mean, median, mode. Mean, median, mode. Give me one of them.
Mean is average.
Mean is average. Mean is average. Good. Median or mode. Either one.
Median is the middle term,
Good. The middle term in an ordered set of data. Middle term in an ordered set of data. And mode? Mode?
the number that repeats the most.
The most frequent number. Use the word frequency again. The most frequent number. All right. This next term is something I want to talk about for a little while that I'm going to go into a good amount of detail about. Because it's a term that is, I think, misused and misunderstood by a lot of high school students. Standard deviation. Standard deviation. Forget standard. Deviate. Define deviate.
To move away from
To move away from the norm. To deviate. You say you deviate from the norm. Move away. Good. From the norm. So the norm. In math, the norm is like the average. Okay? So we're going to see this a lot with what are called normal distributions. That's your next slide you're going to see is the term normal distribution. But the standard deviation is an acceptable value away from the average, above or below. So I might say that the average radius of all soccer balls is, I know baseball's diameter is, no. Baseball's, what is it again? Oh, jeez, I forget. What's a baseball? 9 centimeters across, I think? I forget. Let's say it's the average of an object, its diameter is 9 centimeters. Good time. And the values can deviate by 1 standard deviation above or below those values. Above by a certain amount, below by a certain amount also. So this concept of standard deviation is something that is changing about the norm. How much it changes by. Let's specifically see its application with normal distributions. How many of you, anybody here in AP Stats? How many are in pre-calc? Any of you in discrete? Okay, so are you all in pre-calc? Is anyone not in math in this room? So everybody in here is in pre-calc? Oh, good, that's easy. So you don't even, I don't think, discuss this. So I'm going to assume no prior knowledge. Whereas last year, I had 3 students from stats in here. So it was like they knew exactly what all this was already and they were way ahead. So I'm going to assume no knowledge of this, okay? I think we did.
In with Mr. Hall.
Oh, awesome. So you did already start talking about it. Good. So you know a bell curve, right? This is the whole concept? Good. So this is the average, X bar. Yeah, the SAT is by hundreds, you know. Okay. So on the SAT, that's a prime example, a great example. The average is a 500, and every standard deviation is 100 more or less. So a standard deviation is simply X bar plus sigma. Did you learn this notation last year?
Yep.
500.
Really?
Hmm?
500
Because 200 to 800, that's what it ranges. Per section.
Oh.
Yeah, per section, sorry. So each section is out of 800. The lowest you can get is a 200. The highest is an 800. The middle is 500. So if you get a 600 on the SAT, you fall 1 standard deviation above the norm. If you get a 700 on the math, or one part of your SAT, you're 2 standard deviations above. If you get an 800, you're actually 3 standard deviations above. You're the top score, really. Okay? Now, specifically, did you learn about your areas and percentages?
Yes.
Yep.
Anybody remember this first one?
The middle one? Oh wait, are you talking about the middle one or the end?
You tell me either the whole value of these or this segment or this segment. What is the area? One of them is what?
That was 13. That's like the
The
simplest.
last one is like 0.01.
Yeah.
Oh, isn't it like
You're on the right track, but I'm asking you again. What is this one right here?
32?
Sam?
Right, 36.
Take a guess at least.
I thought it was like 33.
It's close. If that's actually close. What is it? 33.1. Is that what it says on there? No. When I was in school, I was taught that it was 68% amongst these two, which would make each of them 34%. That's how I learned it. I don't know how Mr. Hall taught you. I'm assuming he taught you the same numbers, but when I was taking this in college, I remember being 68%. 68% of the data. 68%. What is that approximately as a fraction? Approximately. What fraction is close to 68%? Thank you, Miles. What common fraction that we learn about?
7/10.
Close to 7/10, but there's another fraction that we can reduce that's kind of close to 68. It's really 66.6%. What's that?
2/3.
About 2/3. That's an easy way to estimate. About 2/3. 2/3 is 66.6 repeating, close to 68. Close to 68. So about 2/3 of the data falls in this range for normal distributions. That means that 2/3 of the students that take the SAT on a given day fall between a 400 and a 600 on each individual section. So if you get a 450, you're a little bit below the norm, but you're still within those 2/3 of people. Now, there are other deviations, and these honestly I don't even remember, but you have another second, and then usually a third is the furthest you go here. Okay, I don't think you went beyond X bar plus 3 sigma. This is X bar plus 2 sigma. This is X bar plus 3 sigma. What am I saying right now? I'm saying this. Okay? So this third one is like, this one here, X bar plus 2 sigma, I think it's like 95% of the data falls between here and here. It's like 95 or something like that. Is that correct? Do you remember? Maybe? You have no idea? Okay. I'm pretty positive that between those two red lines, 95% of the data falls. And then finally, the other one is between like the two blue lines, and that was like 99.7 or something like that percent of the data, or 97.5. I forget which way it is.
Yeah.
Something like that. Okay. So what's happening though? Normal distributions are usually used for large sets of data. Why do we need a large set of data?
Because we would have enough for the percentages to work out the actual. Because
What happens if you only have 7 data points?
there's not enough to fit the bell.
I mean, there is, but what's going to happen to you?
It's not a good example.
Why? What would happen to the bell curve in that case?
It'll be all over the place.
It would be all over the place. More specifically, what would happen? It would be skewed. Thank you. There's the word. It would be skewed in one direction or the other. So if there's a little bit more data on the upper side, it would be a normal curve that looked like this instead. I'll draw over it in blue. Ever seen that? That's a skewed to the right data set. Data that's skewed to the left would look like that. Okay, the red one is to the left. So given enough data, most distributions become normalized. And actually last year, I had a big enough class. I had 16 last year in this class. And we actually took the height of everybody in the room, distributed it normally, and it turned out, it was amazing, that if we found the standard deviation in Excel, which we'll do this, and it's probably not going to work well with 10 people though, but we found the standard deviation, and we actually found that about 2/3 of the class was within one standard deviation above or below. And that's exactly or approximately 68% of what it should be. Would it what?
That might work out.
It may or may not, but it's a small set of data, so the probability of it working out is lower for sure. Oh, just looking around? Possibly. We could actually tell. All you'd have to do is stand up and take a look at your heights. Yeah, we'll do it, but we'll do it in Excel. Give me a little bit. Because I'm not gonna ever have you calculate standard deviation by hand. Did you do it by hand in math class?
Yeah. Are we at the
Square root of x minus x bar squared, all that whole thing? Yeah, it's fine to do that, but I'm going to have you do it in Excel because nobody in today's day and age is going to be calculating standard deviation by hand. You're going to always do it in Excel. You're going to type equals STDEV, and you're going to put in your data set, and it will calculate it for you right there. All right, so Caroline, while you were gone, I covered the rest of math, right triangles. I skipped Excel to wait for you to get back to do that, and then we went into statistics just now. So at this point, let's stop with math. For rates of change, what we want to focus on. Guys, what are you doing? Don't worry about it for now. Come on. That's why I said don't worry. Just close your laptop and pay attention up here. So for rates of change, I want to talk about three things. First, the definition of slope. In your math class, you all know what slope is. It's one thing changing as a function of another. That's all it is. One thing changing as a function of another. So you learn about slope as the change in y over the change in x. And we talked about how in physics, it's really the change in anything over something else. For example, if we're talking about velocity, what's velocity really? The change in the object's
Mass.
Oh.
No.
Very good, Sam. The change in an object's position or displacement, very good, over time. So this is, again, a function of time here. In engineering, you'll learn more about like flow rates or anything that's a function of time. Almost everything is a function of time in life. Even your behavior is a function of time. Everything. The temperature is a function of time. The volume of this, or the population in the school is a function of time. It is constantly changing. Things are functions of time. So in this class, what I want you to really be focused on when it comes to slopes and rates of change are things that change as functions of time. And the way to notice that is that the formula will always be divided by t. Anything over t. So if you're looking at the amount of mass flow rate, you're in AP Bio, right?
Yes.
So in AP Bio, you're going to talk about, you've probably talked in Bio about osmosis already and the concept of it, like way beyond. But you'll probably talk about what's called volumetric or mass flow rate as far as equilibrium. So the amount of mass flowing in and out of a cell membrane. So that would be in physics or in engineering, we call that m dot. And m dot simply means the mass as a function of time. So it's things as a function of time. So in this class, when you think of rates of change, I want you to be thinking of functions of time. Okay, you go to a gas station, or you fill up your car, you start driving, gallons per minute. Or the flow rate that comes in your car is in gallons per minute. The amount of usage of the car is in maybe miles per gallon. That's not a function of time, but that's a function of the amount of fluid as a function of the actual distance itself. Let's see. What else? This is something that I kind of jumped into last year, but I think some students had struggled with it, but just to give you an idea, if I wanted to plot and figure out, let's see. If I wanted to plot f as a function of m2 here, I would see that this quantity right here would be my coefficient in the front. m2 is the thing that's changing, f is the force of gravity, G, M1, and R squared are the things that are constants. Well, what you're going to notice in class here is that if you were to plot F versus M on this line, and then you would actually fit a linear function, the slope of this linear function would be GM1 over R squared. And again, look at this, make sense of it. Linear functions are y equals mx plus b. M is the coefficient. Gm over R squared is now like a coefficient. So if you plot m on the x-axis, or horizontal, and f on the vertical axis, what does the slope become? This m is not mass. I hate that m is used in math so often. We use a. Okay, doesn't matter. I use the word slope. And so the slope is this coefficient, whatever is in front of here. So whenever you want to determine the slope of a line, or what the slope significance is, it depends on what you're actually plotting. So we will probably get to an example this year where we talk about drag force and terminal velocity. We didn't really talk about that in physics last year. That involved a lot of air resistance. So when we do that, did you guys ever see Mr. Donachek do this little thing with coffee filters? Did you ever see him stacked up over there, though, in the beginning of the year? He does a little lead. It's actually really cool. If you drop a coffee filter, it reaches terminal velocity within like a half a foot, where most things don't reach terminal velocity. Because terminal velocity, the idea is that the amount of friction pushing up is equal and opposite of the weight pulling down. So when you drop like a bag of, I don't know, a bag of lemons out the window or something like that, I have no idea, I'm just picking up some ridiculous. You drop a bag of lemons out the window, it's going to get faster and faster and faster, right? Until it reaches what we call terminal velocity. But that would take a long distance for that to happen. Yeah, off the Empire State Building, it reaches terminal velocity way before it reaches the ground, which is why that myth of like killing the penny's a myth. Because the penny itself would start to tumble, the air resistance would increase, it wouldn't
Also,
actually.
you're blown back towards the building and it gets stuck on the, like, there's like sides of the building that it gets like stuck on. So even if it was like a pole.
True, it would probably get pulled toward it as it falls down because it's streamlined. But besides the fact, the concept of terminal velocity, we're going to see that it's a group of parameters that are needed. So I do this as like one of our labs this year. So I wanted to make sure that we get this concept that whatever the coefficient is in front of x is the slope. Well, this is the coefficient in front of m2. So this is really the slope in this case. On Friday, you have to have that Excel homework in. If you don't have it in, it's going to be a 0. It's not going to be accepted late. You've got a lot of time. Do it tonight so you can ask me questions tomorrow. Do not do it Thursday night and email me Thursday night. I will not answer on purpose. Okay, no, but you could see me at any point. Tomorrow, Thursday, you can ask me as many questions as you want, okay? Put the laptops in correctly, please.